objectives for today, you can see them up on the board. By the end of the notes, you should be able to explain how stars produce energy, describe the structure and composition of stars. So composition, what's it made of? Structure, what are the layers? And then also be able to classify stars based on their color, their temperature, their mass, and their luminosity. Okay, so those basically 4 pieces are going to be used in a system to put stars into different groups. You'll need to be able to know what group a star belongs in. If we get to the end of the notes and you cannot do that, you need to come talk to me because you missed something. Okay? All right. How stars shine. So we're tackling the first objective right now. Stars are made up of gases, and those gases are at really high temperatures and really high pressures. The core of a star is so hot and so high pressure that those particles are moving incredibly fast and with a lot of force, and when they run into each other, they're capable of undergoing a process called nuclear fusion. Nuclear fusion is when 2 nuclei from different separate atoms get smashed together and become one nucleus. And it's a larger nucleus because now there's more protons and more neutrons, okay? This process releases a large amount of energy as both heat and light, which is how stars produce energy. Now let's talk about composition and structure. Most stars are made up of 2 gases, hydrogen and helium. Now, notice I say most. There are stars that have other gases in them, but these 2 are the most common, okay? And the reason that they have helium and not just hydrogen is, remember, we just talked about nuclear fusion happening in the center of these stars. What happens is that hydrogen is fused, so 2 hydrogen nuclei are fused together. When you do that, you go from having 1 proton to 2 protons, which according to our periodic table means you go from being hydrogen to being helium. So they are actively turning their hydrogen into helium. So they're made up of those 2. Over time, the percentage of each gas is going to change because hydrogen is going to be continuously converted into helium. In general, stars have the following layers, or zones, you could call them. We're going to start from the inside of the star and work our way out. So the inner layers are the core at the very center of the star. Okay? This is where the process of fusion is happening because it's where there's the most heat and the most pressure. So that means at the center of the star is where hydrogen is becoming helium. And because helium is more dense than hydrogen, it doesn't escape out of the star, but instead it gets sucked down and stays in the core because it's denser than the hydrogen that surrounds it. Just outside the core, we have a layer called the radiative zone. This area has hydrogen that's slightly cooler than the core, and there are so many hydrogen atoms packed into the radiative zone that when energy is leaving the core and moving through the radiative zone, it actually moves incredibly slowly because it's constantly running into hydrogen particles and being bounced around. So energy exiting the radiative zone takes a while. And then the last of the inner layers is called the convection zone. This is just above the radiative zone, and hot gases here move to the surface. So hot hydrogen from the inside is moving to the surface because it's less dense, so it's rising. And cool hydrogen from the surface is moving inward because it's more dense, so it's sinking down in. And in the convection zone, light energy and heat energy are able to move up and out quickly because there's fewer hydrogen molecules. Okay. Now, I want you to understand something. When I talk about hot and cool hydrogen here, it's all hot compared to what we're used to. But relative to each other, some of the hydrogen is cooler and some of the hydrogen is hotter. But in terms of our temperatures, it's all very, very, very hot. All right, now let's talk about the layers that are outside of those inner layers. So we went core, radiative zone, convection zone, and then immediately above that, we have the atmosphere of the star. Okay, the photosphere is the layer that appears to be the surface of the star. So when you look up at the sun and you see the sort of round surface shape of the sun, what you are seeing is the photosphere. Okay? It appears smooth to us as we look at it from a great distance away. You shouldn't be looking directly at the sun, but I'm sure you've seen pictures of it. It appears smooth, but it's made of gas, so we know it's not going to be like entirely smooth. Above the photosphere is this reddish-orange layer that we call the chromosphere. Not a lot of information related to what the chromosphere is. It's just a reddish-orange layer of gases that's immediately above the photosphere. Okay? And then outside of that is the corona. Okay? The corona is by far the widest layer of a star's atmosphere. It's on the very outside, and sometimes the corona of a star can stretch several million kilometers. Okay? Believe it or not, some pieces of the Earth's corona, or of the sun's corona, can actually interact with the Earth, even though we are 150 million meters or kilometers from the sun. So, this layer is big. Now these layers of a star, the internal layers and the atmosphere layers, these layers don't necessarily change very much. They can take millions of years to undergo large changes, okay? But there are some aspects of stars that can change more rapidly. And we're going to discuss some of them, but we're going to discuss them in reference to our star, the sun, because it's the closest and it's the one we have the most information about because it's close enough for us to study it. So when we talk about these changing features, we're talking specifically about changing features of the sun, okay? The external features of the sun can change. Sometimes it takes years for them to change. Sometimes it takes months for them to change. And sometimes they can even change in minutes. Some common changing features of the sun are sunspots. Sunspots are regions of strong magnetic activity, and as a result, they're much cooler than the rest of the photosphere. So they appear, when you take images of the sun, to be dark spots on the surface of the sun. Sunspots come and go. They reach their peak every 11 or so years, and then they decline and come and go. But there's usually sunspots on the sun. It's just how many changes over time. Then we have things called prominences and flares. So a prominence is a cloud of gas that makes a big loop or a jet, and it extends up into the corona of the sun. And then a flare would be a sudden increase in brightness of an area. This usually happens near a sunspot or near a prominence that's happening. That's why we looped them together. Then we have things called coronal mass ejections, or CMEs. These are huge bubbles of gas that actually get ejected from the corona, so pushed off from the corona, and they can travel towards Earth. They are much larger than flares, and like I said, sometimes when they are ejected, they can reach Earth, and when they do reach Earth, if they're of a large enough size, they can do things like cause a radio blackout. They just affect radio waves. And then they can also cause satellites that are in the Earth's orbit to malfunction if they get hit by them. It's not a permanent thing because, like a wave, it passes over us and is gone, but they can reach Earth and cause real impact to us. And the last one we'll talk about is solar wind. Solar wind is actually a thing that's continuously coming to us from the Earth. There are these charged particles that stream away from the sun continuously. And obviously we would assume they stream in every direction, but when they hit Earth and they interact with our magnetic field, they create what we call the northern and southern lights. the aurora borealis and the aurora australis. So they cause those pretty patterns of bands of light that appear in the sky. All right, next up we're going to talk a little bit more about stars other than our sun, okay? There are groups of stars that appear in the sky. Now, there are some stars like our sun that are just solitary. They're out there on their own. So that's not that uncommon. The most common group of stars would be binary systems, which is where you have two stars that are orbiting each other. So they're out there together as a little pair. Okay, so that would be the most common group that you would find. And then there are also stars that tend to group together in large groups. And when they do, we have two types of star clusters that we talk about. If it's an open cluster, then there are relatively few stars in it, only in the thousands. Whereas if you have a globular cluster, then that's going to contain hundreds of thousands of stars. A cool thing about groups of stars is that when stars form in clusters, usually what happened is they formed around the same time and in the same location, which means they should be the same age and they should be the same distance from Earth. So if you identify the age and the distance of one star in a cluster, then you have identified that for all the stars in the cluster, which helps us significantly because determining distance and age when stars are that far away from us is not always easy. So it's nice to be able to group them like that. So now we've covered our first two objectives. We know how stars produce energy, and we've discussed what they're made of and how they're structured. So now it's time to hit that very last objective, which is learning how to classify stars. Okay. Scientists classify stars based on their colors. Okay. But because color is related to the temperature and the size of the star and how bright they are, those things are also usually included along with this. But you'll see that the classifications is basically listed on their color and their size or their mass. Okay. Take a look at this diagram right here. Okay, you have it in your notes, so it's not going to disappear when we go to the next page, but it'll disappear for me. So if you look at your diagram, here is the listing of stars from left to right and how they're classified, okay? So all the way on the left, you have the smallest and dimmest and coolest of the stars, the red dwarfs, okay? They are named for their color, red, and for their size, dwarf. Immediately to the right of the red dwarf stars, you will see some orange stars. Okay. We usually only have small orange stars, so I suppose you could call them orange dwarfs if you wanted to, but our book just says orange stars. Okay. Then we have yellow stars. There are yellow dwarfs and there are just plain yellow stars that are slightly larger. Our sun is the smaller of the two, so technically our sun is classified as a yellow dwarf star. So in terms of overall size, the sun is actually a pretty small star, right? But it appears rather large to us because of how close we are to it. Then to the right of the yellow stars, you can see the two different sizes of white stars. So you can have a white dwarf and then a regularly sized white star. And then you can see the blue-white stars. These are the largest and brightest and hottest of the stars, and they tend to be pretty big. Although, again, you could have some that were smaller. So this would be how we classify stars based on their color and their size, but we also sometimes take into account their luminosity. Okay? So you can look at the next image that you have. Okay? This is a chart or a scale made up by two scientists, and it's named after them. Okay? It's called a Hertzsprung-Russell diagram, named after the last names of the two scientists who came up with it. And they wanted a way to organize stars based on their temperature and their luminosity. So you can see on the diagram that on the y-axis, we increase luminosity as we go up. So stars get brighter. Remember that luminosity is absolute magnitude. So this is their actual magnitude based on how we measure them by heat and size and temperature and things like that. Heat and temperature, same thing. But on the x-axis, as we go across the x-axis from left to right, we are decreasing in temperature. And when you plot existing stars by increasing luminosity and decreasing temperature, you get this band in the middle that forms, that goes from the top left and kind of curves down to the bottom right. And they call those stars the main sequence stars. So this is what we would consider to be like a quote-unquote normal star, a main group star. Okay? The sun is essentially right in the middle of that band in those yellow stars. Okay? But what I want you to notice on this diagram is something important, is that some stars are either up in the top right or down in the bottom left. And those stars are stars that use up their hydrogen more quickly. And then they move off of the main sequence line and become either a giant or a dwarf. And we will learn about the life cycle of stars and how this can happen in the next section. But for right now, all you need to know is that these stars exist. That should be the end of the notes. And if it hasn't already, then in just a moment, your homework, the 12.2 Check for Understanding, should be posting.